Hi. In this problem, we're going to get more practice working with densities and also working with conditional densities by conditioning on an event. The density that we're given is one for a random variable x, and we're told that the density is x over 4 when x is between 1 and 3, and otherwise it's equal to 0. So here I've drawn out this density. From 1 to 3, it's x over 4. So it goes from 1/4 to 3/4, and outside of that, it's 0. And we're also given a definition for an event A, which is the event that this random variable x is at least 2. So think of it as, here's the line where it's 2. A is the event that the random variable is greater than or equal to 2. And now, in part A, we're asked to find a bunch of things. The first one is the expected value of x. The expected value, remember, the definition is this integral. You integrate x times the density of x. And the important thing here to remember is that when you plug this in, when you plug in the density, which is x over 4, you need to remember that to correct the limits, because this density is only valid from x equal to 1 to 3. So instead of integrating from minus infinity to infinity, we only go from 1 to 3, because outside of that range, this integral is actually 0, right? Because the density is 0. All right, so now it's just some solving this integral, which is x squared over 4 from 1 to 3. Okay. So what exactly is that? That's going to give you, pull out a 1/4, you integrate x squared, that's 1/3 x cubed from 1 to 3. All right, so that's 1/12 times 27 minus 1, which gives you 26 over 12, which you can also further simplify, 13 over 6. All right, so that is our first answer. And we can actually, let's just check that this kind of makes sense. This is a little bit over 2, right? So it's somewhere here. And yes, that makes sense because it makes sense it's a little past 2. If this were flat, if this were uniform, then we know that the expectation would be exactly the midpoint, which is at 2. But this density is actually skewed more towards higher values of x, right? So you would expect that the expectation is actually to the right of 2, a little bit higher than 2. So that seems to check out. The next thing to calculate is the probability of this event. The probability of the event A, which we can also write as the probability that this random variable is at least 2. All right. Now, how do you calculate the probability the random variable is at least 2? It's just a matter of integrating the density. And you integrate the density from 2, starting from 2, because you want it to be at least 2, and you integrate it all the way to up, in general, it would be to infinity, right? But we know that for values of x greater than 3, the density is 0. So we actually just integrate from 2 to 3. Really what we're doing is we're just calculating this part. So we can just, again, plug in what this is. It's an integral from 2 to 3 of the density. And in this range, this formula holds, so it's x over 4. And now that's going to give you 1/8 x squared from 2 to 3, right? So it's 1/8 times 8, times 9 minus 4, which gives you 5/8 as your answer. And again, we can check that this kind of makes sense. The probability that the random variable is at least 2 is 5/8, which is a little bit more than half, right? And again, we can compare this to the case where it would be uniform. If it were uniform and flat, then the probability that it's greater than 2 would be exactly half, right? Because it's symmetric. It's half on this side, half on this side. But because it's skewed, again, more towards larger values, you would expect that the probability that it's at least 2 to be a little bit more than a half. And the probability, similarly, the probability that it's less than 2 would be a little less than a half. All right, so that also checks out. Now, let's actually calculate the next thing, which is the conditional density of x given the event A. So what does it really mean? It means now, by conditioning on A, we're saying that we're in this the universe where the random variable is actually at least 2. So instead of focusing on the original density, now we're actually just in this restricted universe of just this part. And now we want an updated density for only this part. And in general, what really happens is you just take the original density that held for the entire random variable and rescale it, right? Because if you just took this, it wouldn't be a valid density because we know that this part of the density only integrates to 5/8, and you need a density to integrate to 1. So what do? We take the original density and rescale it so that it does integrate to 1. And what that amounts to is really just taking the original density and dividing it by the probability of A, which is the probability of this portion of the density. And you see that it exactly is the normalizing factor that we need in order for this to integrate to 1. And again, we need to be a little bit careful because this is only true when x is within A. In other words, when x is between 2 and 3. And otherwise, it would be 0. Okay. Now, we know what these things are. The density, the original density, is x over 4, and that was valid from 1 to 3. And we're in 2 to 3, so that's still valid. So it's x over 4. And then probability of A, we calculated earlier, is 5/8. So when we divide that by that, we get 8/5. And so when you simplify this, you get 2x over 5. And that becomes your new density. And we could actually also plot out what this is, and it would actually look something like this. It would be this portion of the density. So notice that now it's 2/5 is a slope as opposed to 1/4. And really what we've done is we've taken this and rescaled it so that this trapezoid now integrates actually to 1, whereas this portion of it only integrated to 5/8. Okay. Now, for the last part of this part A, we're asked to find a conditional expectation. So condition on the event A, what is the expectation of x? Or put in other words, what is the expectation of x given that we know that it's at least 2? Well, we know that when we calculate expectations, the general form is something like this kind of integral, right? But because we're conditioning on A, we have to change the density to the conditional density. So we integrate, as before, x, and we use the conditional density, which is 2x over 5. And now we need to be careful because, again, the limits in general are in -infinity to infinity, but we need to write the right ones, the ones that are valid for this expression for the conditional density. So 2x over 5 is only valid from x from 2 to 3. So we integrate actually from 2 to 3. All right. So what is this integral? It's 2/5 times the integral of 2 to 3 of x squared. Right? So it's 2/5 integral 1/3 x cubed from 2 to 3. So it's going to give you 2/15 of 27 minus 8. So the final answer that you get, this gives you 19 times 2 is 38 over 15. And you can see that if you look at this, this is 2 and 8/15, which is a little bit more than 2.5, right? And again, if we're in the conditional world where x is at least 2, or effectively where x is between 2 and 3, and if in this conditional world the distribution were again uniform, you would expect this conditional expectation, to be 2.5 exactly, the midpoint. But because just like before in the unconditional world, in the conditional world we still have the case that it's skewed more towards 3. So because of that, it's a little bit more than 2.5. So it's actually 38 over 15. 38/15, which we can, again, just do a quick sanity check to make sure that our answer makes sense. Okay. Now, one last part. Part B. Now we introduce a new random variable, y. And we define it as y equal to x squared. And we are asked to calculate some things. So first, let's calculate the expected value of y. Well, to use the standard way, we would have to calculate the PDF of y and then use the integral formula, right? But in order to do that, we would need the PDF of y, but we don't actually know what that is. But because y is related to x, right, we can actually just write it in terms of expected value of x squared, because y is x squared. And now this is just, we use a formula, right? The expectation of a function of a random variable is the same thing, because and so instead of writing just x, we write the function of x. So it's x squared times the density of x. Right. So that's the general form. And now let's actually plug it in and see what it actually is. The density, we go back to the original case, is x over 4. So we get x cubed over 4. And now also we need to update the limits. This density is only valid from 1 to 3, so we have to integrate from 1 to 3. So when we do this integral, what do we get? Well, we get x to the 4th over 16 from 1 to 3, which gives you 1/16th, and then you get 81. Right? 3 to the 4th is 81 minus 1. So 80 over 15, or sorry, 80 over 16 is exactly 5. Okay, so even though we don't know exactly what the distribution for y is, we can use what we know about x to calculate the expectation of y. Now, the second part is we want to find the variance of y. And again, the usual formula is expectation of y squared minus expectation of y quantity squared. Now, we already know what this is. Expectation of y, we just calculated, is 5. But we also need to know what the expectation of y squared is. And we can use the same method here, because y squared is just x to the 4th. Right? So expectation of y squared is just expectation of x to the 4th. And now we can use the exact same sort of formula to calculate what that is. So we integrate x to the 4th times the density of x. We plug that in. The density of x is x over 4, so this becomes x to the 5th over 4. And then, again, the formula, the limits we need to be careful of, goes from 1 to 3. So when we do out this integral, we get x to the 6th over 24 from 1 to 3, which equals 91 over 3. So the last part now is just combining the pieces. The variance of y now is just expectation of y squared, which is 91 over 3, minus expectation of y quantity squared, which is 5 squared is 25. And that gives you 16 over 3 as your final answer. Okay, so this problem really was kind of a drill problem that started out with giving you a density and asked you to calculate a variety of different quantities related to that density. And then we also added another wrinkle into it by conditioning on an event and working with a conditional density. The last thing was coming up with a related random variable and using the original random variable to help you calculate quantities related to that new random variable. Okay, so we'll see you next time.